Let us practice the linear algebraic equations that are homogeneous. Consider the following three equations for these three unknowns. So we write the augmented matrix of the system. Namely, we copy the coefficients 1, 2, 3 and the right hand side. Then the second equation gives the second row, namely 2, 0, 1, 0. And finally, the last equation writes the last row, 3, 2, 4, 0. Well, and we bring this matrix to the upper triangle form by Gaussian elimination. So we copy the first row, 1, 2, 3, 0. And then to get rid of 2, we take the second row and we subtract 2 times the first one. And we have 2 minus 2 is 0. 0 minus 4 is minus 4. And 1 minus 6 is minus 4 and 0. And here we take the third row and we subtract 3 times the first one. 0, 2 minus 6 is minus 4 and 4 minus 9. Oh, sorry, something is wrong. No, here we have 2 minus 6, sorry, 1 minus 6 is minus 5. And here we have 4 minus 9 is minus 5, 0. And now we see that the third row is just the second one. So if we subtract, we get 0. So we can cancel this row. At this point, the matrix splits into 3 parts. We have the right-hand side column on the right. This is a column of its own. Then we have a square block in the upper triangular form on the left. And in the middle part, we have one column, and for the unknowns corresponding to the columns in the middle part, we can choose any parameter. So we can choose, say, z is t, and then the second row becomes minus 4y minus 5z, but z is t is 0. So 4y is minus 5t, so y is minus 5 over 4t. And the first equation becomes x plus 2y, but y is minus 5 over 4, so we have minus 5 half t, plus 3z, but z is t, so plus 3t, this is 0. So x is, this is 2.5, so this is 1/2 of t, so this is minus t half. three lines together, we can write the vector x, y, z, and this will be x is minus 3 half, y is minus 5 over 4t, and z is t. Or we can factor out t, and we can write the vector minus 1 half minus 5 over 4, 1 times t. Well, and this can be interpreted graphically that in the three-dimensional space x, y, z, the set of all the solutions forms a straight line going through the origin, because when t is 0, we have 0, and this vector gives the direction of the line. Well, some line going through the origin. So you see, even a homogeneous system, or even a homogeneous system, has always a zero solution, but it may have also a non-zero solution. So consider once again the homogeneous system, and if the matrix is square matrix, then we say that the system is square, so we consider a square system. That means the matrix is n by n. So the homogeneous system is always the trivial, the zero solution. And what about the non-trivial solution? If we go back to our system with one equation, if we have just a 1 by 1 matrix, is it possible that this equation has a non-zero solution? Yes, it is, if a is 0. And similarly, we can have a non-trivial solution here if the matrix A is 0. That's correct. But this is too strict. You see, this matrix is not 0, and still it has a non-zero solution. So it is not necessary for the matrix to be completely 0, meaning each entry being exactly 0. What is completely sufficient is that now stop me and try to formulate this condition yourself. Okay, let's try it together. The square system of linear algebraic homogeneous equation has a non-zero solution if and only if, the determinant of the system is 0. Once again, a square, linear, homogeneous system of algebraic equations has always a 0 solution, and it has a non-zero solution if and only if the determinant of the system is 0. We can verify this. This system, this determinant, if you forget this determinant is 0 because it has rank 2. If we compute the determinant just separately, 1, 2, 3, 2, 0, 1, 3, 2, 4. Then we have 0, 6, plus 12, minus 0, 16, plus 2, which is 18 minus 18, which is indeed 0. Well, also you can see that the third row is just the sum of the first and the second row. You see, 1 plus 2 is 3, 2 plus 0 is 2, 3 plus 1 is 4. So if the third row is a linear combination of the other rows, they are linearly dependent and the determinant is 0. And this is a necessary and sufficient condition for the existence of the non-zero solution. There is if and only if. The square system has non-zero solution if and only if the determinant of the matrix is 0.